Thank you, Sanchez, and a very good afternoon to all of you. It is like opening the innings in the open gallery. So let me try to make you not sleepy. So I'll be presenting on our work on behalf of my team. The work is on carbon MEMS. That CMEMS stands for carbon MEMS, derived glassy carbon electrodes as sensitive electrochemical biosensors. So in this work, I'll mainly focus on the fabrication techniques of these carbon electrodes as well as its application on the bioelectrical format. So my talk will be following these points like motivation of the present work, fundamental limitations, material and methods, result and discussion, and finally I'll conclude it and acknowledging the people I got help from my institutes. Now, from the title, you can understand that what we are doing, we are using carbon MEMS technology to make electrodes. And those electrodes are very much biocompatible material to sense some disease to diagnose it. Now, nowadays, you might be knowing that we are attacked by many viruses. The viral attacks we need to identify at the right time, otherwise it could be very fatal to the mankind. And those are, you can see that hepatitis B, hepatitis C, HIV are many of them. So the motivation came like that. The people who are staying at the villages, the country like India, who does not have access to the hospitals, or even so, you can understand that if there is no such access to the hospitals, so how can they survive of that kind of attack? So there is a government of India program who are investing money to make such a device which can be working in the village condition where money is not a factor. It will be very minimal amount of money will be invested to do those kind of tests. Now those tests will not be that might be specific. It will be yes or no kind of test. So preliminary test can be done. So motivation came from there. Now this is not very new. There are already existing technology and it is called ELISA. But ELISA is suffering because of very poor detection limit. Also, you need to spend more money for that kind of testing. So we thought of doing such kind of, developing such kind of devices. And we thought of going for electrochemical biosensors. That electrochemical biosensors is also, it is not so new. Still it is available in the market. But it is for point-of-care diagnostics. I think you might be knowing about point-of-care diagnostics. It is still not for the common people. It is in one umbrella there will be several big, huge instruments will be putting, but in the under one umbrella. So we are thinking about making it for extreme point-of-care diagnostics, where you can carry the instruments to the place where people need that access. And to do so, you need a very handheld and portable system. Not a big system, you can't carry that one. So we thought of making a CD platform. So this is extreme point-of-care diagnostics based on CD. CD is a compact disc. So it is now going to be obsolete, but we are trying to make it alive to use for biomedical applications. So you know all these things, the clinical lab reports and all these things are actually increasing the cost of the diagnosis. So we would like to make such a CD platform where you can make microfluidic channels on this CD so that you can reduce the cost because the fabrication of that CD is not so high. As well as it will be very portable. It is a small system. I'll show you in the last of my presentation, the small video where we have already made a spinner system. It is a very small and handheld system. Also, you can do multiple tests on a single CD. So you do not need to waste a CD also. The detection will be very fast and minimal instrumentation is required. So as I said, you should make a system which can be used at the place where it is needed. So people will not be that much educated to operate that one. And it does not require that much education to operate this kind of system. This CD will be 3 to 5 layers. So microfluidic channels you can make in one of the CDs, and there will be 2 layers to combine this 5-layer CD. So to attach, to bond it. So finally it will be look like a compact CD where already microfluidic channels and chambers are fabricated on this kind of CD. Now this is the motivation of that one. And you can use a stepper motor to rotate that one, basically to use the centrifugal force to flow the fluid from one chamber to another chamber. This is also established technology. Samsung and other companies, they are also making a big system again, because they are using optical detection. And you know, to use that optical detection, even it is a small microscope, but it requires a huge space and money. So we are thinking of replacing that optical detection to electrochemical detection. How we can do that? We can use the existing material for electrode, for biochemical, electrochemical sensing. But again, integrating that electrode here, it will be costly and it will not be that much compatible. So we thought of using carbon MEMS technology to make carbon electrode, because carbon is very much biocompatible. Now question is, why not silicon MEMS? Silicon is established one. So there are several reasons. I'm not going in details of that one, because silicon cannot be used for many applications of like gas sensor, like biosensors, nanoelectronics, microbatteries. So we need to look for a different material where we can solve these problems. And carbon is the very good alternative of that silicon. But again, carbon is not a very good material to handle it. It is very much brittle. So we look for a source of carbon where we can handle it very easily. And carbon has a very good source of that, and it is in the polymer form, like photoresist. The people who are working in this microfabrication or nanofabrication, they might be knowing that for photolithography, we use photoresist to pattern it. And we are using a source of carbon is SU8 as the negative photoresist. We can use that one, we can pattern it in the polymer form, and then we can convert that polymer structures to carbon structures using one-step conversion called pyrolysis. So this is the main important step for this fabrication of these carbon structures, that is the pyrolysis. So this is the schematic of the MEMS process, where you can see we are using the conventional photolithography process till this one, and then one step conversion of that polymer structures to carbon structures. Now this pyrolysis process is not new. It is coming from very ancient age, and people are using that this kind of furnaces to make charcoals and all these things. And nowadays it is available in a very sophisticated manner. Now what is pyrolysis? It is nothing but the breaking of bonds at high temperature where you are not supplying any oxygen. If there is no oxygen, the chemical bonds will be broken and you can get carbon-carbon bond, because we are using a polymer structure. So there will be hydrogen, nitrogen, oxygen and several other molecules with the carbon chain in a polymer, that SU8. So we can break all the bonds, or most of them, not all. Few oxygen still will be there, and we can get a carbon-carbon structure at the final stage. So there will be a step of increasing this temperature, because initially hydrogen will be broken before 200 degrees centigrade, and slowly all the other bonds will be broken. Based on this step, you can get a quality of that carbon structures. If you are doing very fast, then there will be chances of getting a porous structures. So it is also very much important of this stage. And we are getting the conductivity of this kind of structures around 2.7 to 10 to the power 4 Siemens per meter. And this is quite good. It is not comparable to all the other metals like gold and others, but it is good for this kind of application. So now back to our work which we have done. So basically we have fabricated electrodes using that carbon MEMS process. First we have made SU8 electrode and then converted it to carbon one. Then the functionalization of those carbon electrodes with antibodies. First we have actually pipetted this anti-hepatitis B antibody. We kept it for a for the physical absorption of this antibody. And then we have used cyclic voltammetry to identify the oxidation and reduction points. And after that, we have incubated that used electrode with hepatitis B antigen in that room temperature for 15 minutes. And again, we have done CV, and we have seen the changes in the current, measured current of that cyclic voltammetry. We have also done the electrochemical characterization using the system Origa Flex. And in this cyclic voltammetry system, we have used this modified or surface treatment electrode as the working electrode, and platinum as the counter electrode, and silver chloride as the reference electrode. And we have used as the electrolyte as potassium ferricyanide and potassium chloride. And CV has been measured in this range for minus 0.9 volt to 0.8 volt with the scan rate of 10 millivolt per second. So this is the structure. This is the schematic of that, where this is SU8 structure, and after conversion it will be look like that. Structure will be remained same, but there will be a shrinkage from side walls as well as from height, because all the other non-carbon atoms have been removed. So you can see this was the initial the top area of that structure, but after carbon conversion it actually arrived here. So I have done this Raman spectroscopy to check its structural orientation of that one, and I found that it is having disordered peak as well as the ordered peak, and it is not the amorphous carbon. So people often misunderstood with the glassy carbon as the amorphous carbon, but it is also having the ordered structure here. So it has many parameters to control the orders. We can control the ratio of these ordered and disordered structures also. Now, to use for this electrochemical sensor, first we have checked its reliability of the single electrode. And with time, we have done several scanning in that electrolyte solution, and we have seen that the current, the peaks, this is the higher peak and this is the lower peak, this one, and it is almost keeping constant for a longer time. And then we have used those electrodes, what I told you, modifying the surface of that one with antibody and as well as an antigen. And we have found the oxidation and reduction voltage are almost same, but we observe that the current value is actually reducing. This is the without treatment, the bare electrode, and after antibody it is becoming like this, and after again treatment, doing treatment with antigen, it is actually reducing that one. And we have observed that the reduction in current is 33% for 175 millivolt application of that 10 femtomolar of the hepatitis B solution, whereas if we are increasing the concentration of the hepatitis B antibody, so the current reduction is 75%. We have made a calibration curve also here. So as I told you, this is a preliminary work to study that whether this can be used as the hepatitis B sensor or not before integrating that one to the CD. And we have made that structure, we have characterized it, and we have found that the detection range of 1 picomolar, 1 femtomolar hepatitis B with the sensitivity of 40%. And with the continuation of this work, we have already done 3 electrode devices, and we have integrated with the CD to measure it for blood impedance to relate with the blood glucose. And just bear with me for one more minute to show you that what is actually we are going to do. First of all, we need to design that CD, and then using that CNC machine, we need to cut that CD. So 3 layers will be made using the CNC machine. And then the 2 layers of adhesive layers will be made using this vinyl cutter. And finally, it will be bonded. That 5 layers will be bonded together to make a compact disc, and one laminator will be used to make it the bond stronger. This is the electrochemical sensor. We can put it here and just giving a solution or the biomarker for the reaction, and after that we can measure the oxidation reaction peak. So this is the biopotential stat. What I was telling, like we cannot even use the conventional potential stat. It is also big and it is also costly. So the image you have seen there, the biopotential stat, also one of our team, they have made it, and finally we'll be using that one as the compact system. So I would like to acknowledge MEC and MEMS lab at IIT Kharagpur, mechanical department at IIT Kharagpur, and Tecnológico de Monterrey, Mexico, and the funding support from imprint grant from MHRD and ICMR. Thank you for your attention.